Welcome to the lecture series for Chapter 9, Multi-Area OSPF. I'm briefly going to summarize what we'll be discussing over the course of the next few videos. This lecture series is going to be a little bit shorter than the one for Chapter 8 because, as I mentioned in one of my other videos, the essential thing about multi-area OSPF is actually getting all the individual single areas working correctly. If they don't work correctly, the whole thing doesn't work. So let's talk about what that's going to mean. So, and I'll be floating about a bit. So, what we're going to do is we're going to talk about multi-area OSPF operation, how it works in the size of network we're usually going to be dealing with, multimedia business sized, how it is used, how it handles leak state advertisement, how it handles neighbor adjacency. The big thing here is that there are some LSAs that we didn't talk about in single area OSPF that we're going to need here. Convert and to extend that farther out, there is an LSA, a type, an intra-area LSA that we haven't seen yet that we'll see until Chapter 10 when we start talking about DRs and BDRs. So we're going to talk about how it works, design considerations, that kind of thing. Then we're going to talk about implementing it, both for V2 and for V3. If you watched the video for 9228 already, great. If you want to watch these and then the lab demos, cool. So we're going to talk about configuring them and verifying them. Really and truly what we do in terms of the thing that makes multi-area OSPF is when you're building your network statements, you're going to think about what area number you give it at the end of each network statement, or what area you declare for each IPv6 interface that you're considering. So let's talk about OSPF multi-area operation. Okay. Now, one of the issues that we can have in a large single area OSPF implementation is that there are too many routers to talk to each other. Remember, the definition of convergence in single area OSPF is every router in the area has the same LSDB. That's a lot of LSAs going around. That's a lot of neighbor relationships potentially forming. Now, of course, each one is only forming relationships with its immediate neighbors. It's not like it has to have a neighbor adjacency with literally everything, but that can still mean large routing tables, large link state databases, frequent and expensive SPF algorithm calculation. So the way to make all of this more efficient is to break that one big area up into smaller areas so that each area builds its own LSDB with fewer devices, fewer networks, fewer interfaces to consider. Basically, we take the problem and we conquer it by turning it into a lot of little problems, scaling it down. OSPF scales up well because it is capable of you're capable of building OSPF using lots of smaller areas. It's like this. Okay, so with multi-area OSPF, you've got your area 0, your backbone area, joining your area 1 and your area 51. No little green men involved. So that means smaller routing tables, smaller LSDBs, fewer link state updates. You're calculating your SPF tree less often. So that reduces our processing time, that reduces our memory overhead. Now, the thing here is it requires a hierarchical network. This point here is very, very key. If your subnetting scheme is chaos and you've got a little bit of say in Area 51, you've got just a random mix of Class A and Class B and Class C. And in Area 1, you've also got a different random mix of Class A and Class B and Class C. And you've got some networks over here and some networks over here that should be all together, because numerically speaking, they're contiguous. That is a recipe for disaster. If you've got a network like that, the first thing you need to do is rethink it from square one. Look at your subnetting scheme. Think about, okay, what parts of my network need to be where? And then go from there. Reprogram your routers, rebuild your DHCP servers, etc., etc., etc. So you have a whole bunch of networks over here which fit in the same numerical space, and a whole bunch of networks over here that also fit in the same numerical space. And so as things are going through Area 0, you have much less to talk about. One of the things we talk about, or that I demonstrated part 3 of Lab 9228, is inter-area summarization. If you have a whole bunch of contiguous networks, or even a whole bunch of discontiguous networks that can be summarized effectively using network aggregation or supernetting, you can do that so that these area border routers don't have to share 5 network statements. They can just share 1, which adequately summarizes the whole kit and caboodle. So this means there is a 2-layer hierarchy. And we're going to learn some new terminology here. So we've got our backbone area, our transit area, Area 0, by definition. Its primary function is to interconnect the other areas. There could be some access layer networks in there, but unless those access layer networks need to be at the core and the heart of your network, maybe you shouldn't do that. Maybe what you need, if you've got some access layer stuff, say for example, important servers, VPN gateways from here and there, or DNS, DHCP, your data center, whatnot. If you have to have something like that and it has to hang off the backbone, what it should probably have is its own area also connected through the backbone. So the backbone is mostly just routers. This is why we call it the transit area, the backbone. If you ever hear of a backbone provider, a level 3 provider, those are the folks who, in terms of the business model of the wider internet, they're the ISPs of the ISP. We call those people the backbone. You can think of a big fat pipe aggregating lots of little networks. Same idea here. The opposite idea is the regular or non-backbone area. Your users and your resources are there. They may be arranged geographically. They may be arranged functionally. Say, for example, if you've got, say you've got a big plant on a campus on one side of town doing one part of your job, say engineering or programming or manufacturing or whatnot. Maybe that's an area unto itself. And on the other side of town, you have your headquarters. Now, technically, some of the routers in that headquarters building might be in the backbone area, but the rest of the user and resource part of that same building might be in a different area because it has a different function. Now, all traffic that is going from one area to another must go through your transit areas. Let's see. Okay, so let's talk about the types of router. I've sort of referenced this already in talking about our topologies. We've got internal routers. An internal router is a router that has all of its interfaces in the same area. A backbone router is a backbone router is a router that has at least one interface in Area 0. Now, it is possible for these things to be in more than one category. So say, for example, looking at our topology, these two routers here in the backbone area that don't have a number, those are internal and backbone routers. Whereas the other two, the ones that have numbers, R1 and R2, those are area border routers because they've got an interface in Area 0 and an interface in Area 51. Router 2 is an area border router. and a backbone router. But it is not an ASBR. Router 1 is an area border router and a backbone router and an ASBR because it's got our link to the cloud. Now, these four networks over here, these four routers over here in Area 1, and these four in Area 51, those are also internal. Those are internal regular area routers. And now I'm going to talk about the OSPF LSA types. I'll be back in just a minute.